Okie dokie. Today we are working through, roughly Lab 2 for Math 1026. So I went ahead and went through the lab. Didn't take too long, but they do a great job of over-explaining some things, which is good, but also it kind of made it confusing in some parts. So I'm going to highlight basically just what you need to do in this lab and how to do it. So starting right off with the Rhino population model. We have this first tab, and eventually they tell you to label it as rhinos. And the whole point of this lab is to practice what's known as Eulers Method. You might think it's Eulers. Eulers sounds better, but it's meant to be pronounced Eulers in my experience. So let's jump into it. So basically all they have you do in this first tab is make time values ranging from 0 to 10, and we're going up by 0.5 each time. So they give you the initial conditions for T and R as 0 and 0.1. I think they list it somewhere in here right there. And so we have 0 and 0.1 for T and R respectively. And then they give you this R prime function, this R prime equation, which we can see right here. So 0.6 times R times 1 minus R. So again, 0.6 times R times 1 minus R. Anywhere we see R in the function, we don't want to type 0.1 and we don't want to type R. We want to click on or type in, so we want to click on or type in B2. Okay, so we enter that function, and then let's talk about this next row. For the T values, the 0.5 comes from creating a little function referencing the previous cell and then adding 0.5. And then once we have that, we can click and drag this down until it fills out all the way to 10. As for the R values, right here is where the R values is where the Eulers method comes into play. So I'm going to get rid of all these, and I'm going to redo it. So Eulers method is basically a way of approximating a next R value. So in this case, R value in general, it's a way of approximating the next Y value using the previous T value, Y value, and then Y prime value. So in this case, T, R, and R prime. So to approximate this next R value right here, we use the previous R value, we add on what's known as the step size, or the delta T. They have it somewhere in here that delta T is 0.5. So we add on the step size of 0.5 times the rate of change, which is the R prime. So we click on the R prime in this case. We hit enter, and this is the R value approximated from these previous T, R, and R prime values. So we can drag this down, and it's going to look weird, 0.127 for all of them, until we drag these down. Again, this R prime will be, referencing this R value to the left of it. So when we drag these down, it should kind of automatically correct everything. That was kind of cool. You see how the graph did that? That was fun, right? That was cool. All right, yeah, let's do that again. Look at this graph one time. So we have the formula, and we drag it down. Nice. All right, that's pretty cool. All right, so that was pretty much it for this one. It's just the Eulers formula, roughly, and then so they have you input the graph. So they just have you highlight the A and B. So if you click on A and drag across to highlight A and B, you go to Insert, and you go to Scatter Plot. You click on this first one, and that's how we've gotten this image right here. So I'll leave it at that. Let's go to the next one, the predator-prey model. So initially, so this looks like a lot, kind of ignore the graph and most of this data here so far. They have you put in these labels up here. So originally it's T, H, L, H prime, and L prime. They give you all these initial values here for T, H, and L. So 0, 0.5, and 1 respectively. And then this 0 and negative 0.5, I'll show you where these come from. These are the actual H prime and L prime equations that they give you. So looking at H prime first, we see in here, H prime is, let me use my mouse instead of my finger, H minus H times L. So H, anywhere you see H, you're clicking on B2, and then, minus H times L, so B2 times C2. You can see the formula up there. So we're inputting this formula, hitting enter, and then likewise for L prime, we're inputting the equation. So you can see, same idea, anywhere you see an H in the L prime equation, you're clicking on B2. Anywhere you see L, you're clicking on C2. But you input that function, and then let's talk t-values here. For these t-values, they want you to go up by 0.1 because your delta t, or your step size, is 0.1. So we can do our little function again. So equals A2 plus 0.1, and then once you have that, you just drag it down all the way to, I think in this case, 10, no, 30. I think it's 10, oh gosh, sorry, 10, all the way to t equals 10. And then let's talk H and L here. So H and L, to approximate this H and L value right here, this is where Eulers method comes into play. So let's give this a shot. Check this out. Bam. I don't need it. You know what I'm saying? We're going to do the previous H value. So let me reword. To approximate the hair or the H value at 0.1, we are using the previous H value, and we add on the step size, again the change in t value, and we multiply by H prime. We hit enter. Do the same thing for L. We use the previous L value plus the step size of 0.1, and then we multiply by the L prime value. Hit enter. And then we should be able to click and highlight and drag both of these down. So we highlighted both cells, dragged both those down, and they're going to look weird until we fill out the rest of these. And these also should automatically fill themselves out as long as we input the first formulas correctly. So let me double check these. Yeah, looking good. All right, and I think that's it for this up until the SIR model, besides the graph here. So at the start of this tab, I mentioned that they were originally H and L. The reason they are hair and links now is because what they do on this graph, or how I got this graph, is I highlighted. So I'm gonna go ahead and get rid of it. I'm gonna highlight A, B, and C. So you click on A, and you highlight across. You click and hold and highlight across. Insert a scatter, and it looks like this at first. And when it was H and L, these just said H and L for the labels, but they wanted you to kind of go a little more extreme and say exactly what it represented. So hair and links, respectively. And then this was just like predator, prey model, something like that. And that's all there is to it. Leave it at that. Yeah. Let's go on to SIR Model 1. So what I'm going to do is kind of talk through what you do for SIR Model 1 and 2, and then I'll do 3 together with you, okay? So roughly, let's look back at 1 real quick. They give you these SIR like base models. This is what you'll use in like practice problems and stuff. They give you the initial time value of 0, S, I, and R respectively. That's why at the top we have 8, 90, 10, and 100 respectively. And then, so they tell you to go ahead and like make these 3 tabs down here for models 1, 2, and 3. I think they made a typo too. They said something about sheet 1 and sheet 2. That's not right because it's like sheet 3 through sheet 5. Don't worry about that. Anyway, so model 1 on this first tab here. You have your initial conditions, T, S, I, and R, and then they give you, again, the formulas for S prime, I prime, and R prime. So you take a moment to type in these 3 formulas for S prime, I prime, and R prime, respectively. Anywhere you see an S, you're clicking on B2. That is the first susceptible value. And anywhere you see an I in these equations, you're clicking on C2. So hopefully that's self-explanatory. I'll just click through these 3 so you can get a look. All right. And then once you have those, we do the t-value. So t-value should go up by 0.2 each time. Again, just A2 plus 0.2. Drag that down. Eventually, they want it all the way to 30 days because they're talking about a month, or I guess 31 days, however you want to look at it. And then let's talk this row of susceptible, infected, and resistant right here. This is where Eulers' formula comes into play. So I'm not going to redo it this time because I'll do it for Model 3. But again, it's the susceptible, the previous susceptible, plus the step size of 0.2, times the S prime value. Hit enter. We do the same thing. I prime is the previous I plus 0.2 times I prime. Hit enter. And then R is, to estimate this R value, it's the previous, there it is, the previous R value plus step size of 0.2 times R prime. Hit enter, and then you would like highlight these, all three, and then you drag them all down to fill out these. And then likewise, once you just have these first three, you can highlight those three and drag these all the way down to fill out the rest. And then eventually they'll make you, like, you'll have a bunch of decimals for these, and so you want to make sure that when you want to make sure they're whole numbers. So the way you do that is by getting rid of the decimals. So you highlight all three columns here, and you go to format, format cells, and under number right here, so not currency, not accounting, under number you type 0 decimal places and hit OK, so that there are no decimals, it's all whole numbers, right? And that's pretty much it. And then they have you highlight all 4 columns and insert a scatter plot. Again, you go to insert and click on this scatter plot here, and then that one there. So we're not going to do that because we have it right here. So just to get a glimpse, the reason I changed it from SI and R to susceptible, infected, and resistant was for the labels here. And then I just labeled this SIR Model 1. That's pretty much it. Let's go on to Model 2. Again, very similar process. The only difference, I believe, is the equations that they give you. So down in Model 2 here, they give you S prime, I prime, and R prime. So what's the same, what's different? So the initial conditions, T, S, I, and R, are the same. They start off the same. And then S prime is different. So again, S prime is here, I prime is here, R prime is here, just from these 3 equations. You know, same idea. Anywhere you see, so one little thing about this, wherever you see S of T, that's just another way of saying S, because I think they, yeah, so like back here they had just S and I. That's the same thing as S of T and I of T. So anywhere you see S of T, you don't want to do S times T. You're doing just like the susceptible value, which is 890, at that time 0. So it's just think of it as S, and think of I of T. Think of I of T as just I. So anywhere you see S of T, click on B2, I of T, C2. All right. And then, yeah. And then it's annoying because right on the end here they did times I, but they didn't do times I of T. Whatever. But that's pretty much it. So then you do the Eulers method for these 3 values, right? And then you make sure to drag these 3 all the way down, these 3 all the way down. Once you do that, you'll then highlight these 4, insert scatter plot, and then you'll get this guy here. So I just labeled that SIR Model 2, and now we're on to Model 3. So let's do it together. What I'm going to do is copy and paste these first 2 rows here. So I'm going to just do Control C or Command C, depending on what you're on right now, Windows or Mac. I'm going to get rid of S prime, I prime, R prime. Looking at Model 3 here, so same initial conditions and delta T. Again, the delta T is the step size, so 0.2. So we'll make sure this is 0.2 by doing the previous plus 0.2. And then we want to input these S prime, I prime, and R prime equations. So let's demonstrate. We'll do equals negative 0.001 times, again, just S times I. So times S times I. We hit enter. I'm going to widen this. We'll do I prime, so positive 0.001 times S times I minus 0.14 times I. Hit enter, and then R prime's the last one. We just have 0.14 times I. All right, so now let's demonstrate Eulers method for these 3. So previous susceptible plus the step size times S prime. Infected, we use the previous infected plus the step size times I prime. Resistant, we use the previous resistant plus the step size times R prime. Now, one little thing to mention. you do not want to, instead of typing 0.2, click on the 0.2 here. The problem with doing that is once these t-values get larger and larger, it'll then be like referencing those t-values as getting larger and larger. Like we want the step size to stay 0.2. So never try to like be like, oh, there's a 0.2 there, I'm going to click on that. Don't do that. All right, so let's watch the magic happen. We're going to drag this down. We're going to highlight all 4 of these. Drag it all the way down. We'll go past 30, that's fine. They say to go to a month, 30 days, but eventually we need to go further for some of the questions they ask later on. I'm just going to do, I'm going to go to 30 just for these. I guess I'll go all the way down, might as well. But what I want to do is only go to 30 for the graph that I make, because the graphs are only for 30 days, I think. So I'm going to start at A1, click on A1, hold your mouse, go all the way down to just 30 days. So looking on the bottom left here, when time is 30, stop there. We'll go to Insert, Scatter. Whoa! Oh, that's right. I highlighted too many cells. Watch this. We're going to change this. We don't need all the S prime, I prime, R prime stuff that I highlighted. All right. Let's bring this baby up here. Or not. Let's do this. It's being so finicky. Come on. Alright, we're going to leave this graph down here. Sorry, it's taking way too long. So we have our graph, and we'll call this SIR Model 3. Alright, so that was pretty much it. A lot of the questions they ask about, like number of susceptible, they're all pretty evident from these values here, but what I do want to talk about are some of the things down here, the more, the real questions. They ask for each model, when does the number of sick people begin to decline? What we're going to use is just the graphs for each one of these. And I'll just demonstrate it with model 1, and then you can apply it to model 2 and 3, models 2 and 3. So starting with, when does the number of sick people begin to decline? What does that mean? Well, the sick people are the infected people, right? And the number of sick people is in orange, or the infected is in orange. And so when does the number of sick people begin to decline? Well, it looks like it's going up, 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 and then it hits this point up here, about 3.4733, and then it starts to go down, right? So it's right at, because they ask when, they're looking for a time value, so that's about 3.4, which would mean between the 3rd and 4th day, maybe on the 3rd day, might be on the 4th day, because if 0 to 1 is the 1st day, 1 to 2 is the 2nd day, 2 to 3 is the 3rd day, 3 to 4 is the 4th day, so maybe somewhere along the 4th day. Yeah, so I would say, on the 4th day sometime, that's when it begins to decline. What is the largest number of people that are sick at one time? So that would be, basically, they're asking what's the max number of infected individuals. So on that day 4, around 3.4, on that day 4, come on, give me that value. See that Y value of 733? That's the number of infected on that day. So at any one time, on any one day, 733 would be the max. So if you're ever unsure, because I was just like guessing on this graph, right? It's hard to tell if it's exact. You can go to your values here, 3.4? And realize that 733 was actually not the max, right? Because looking at this column here, the infected, it's actually at 3.2. So really, it's like the start of day 4, 3.2. The infected is 740. So 740 is the max as opposed to 733 or 737, right? Another fun thing about that, you can look at the I prime values. Keep in mind, I prime is the slope or the rate of change. And so these are positive up until about 3.2. So what that's saying is like the slope is positive, and then it hits that max, and then it starts going negative, 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 negative slopes. Pretty fun. So another little tidbit about that. All right, how fast is the number of people resistant to the disease growing after day 1? So how fast is the number of people resistant? So we're talking about resistant, but because they ask how fast is it growing, they're talking about a rate of change of resistant. And so they say, how fast is the number of people resistant growing after day 1? We look at day 1, which is so after 1 day, so that would be, at time 1. So we look at R prime at time 1, 10.47. That's the answer. So it's growing about 10.5 people a day. So that's the number of people that are growing resistant after that first day or after 1 day. How long does it take for the population to be disease-free? So what does it mean to be disease-free? Disease-free means that there are no longer any infected individuals, no longer any sick individuals. So to demonstrate with this first model, looking at this column, again, this is the infected, we see that after 30 days, still 17 people are infected. So we need to go a little bit further until that says 0. Still there. We got 8 people still infected. Let's go down. 4 people still infected. We're still gone. Let's go a little further. Wow, we're still gone. Got 1. Come on, baby. Still gone. That's a tight one, huh? Will it ever hit 0? There it is. Look at that. So between the days, I mean, it's right at the end. I guess that would be the end of the 55th day, the start of the 56th day. So I would say it would take a full 55 days to reach, no more people being infected, or your population to be disease-free. So 55 days is almost 2 months, right? It's pretty crazy. All right, so then you would repeat the same process for those questions for models 2 and 3. I hope this helps. I think this is about all I have for this. There's one more look at this page, this page. Won't scroll too far. You get the idea. All right, I'll just go back up to the top here. Thanks for watching. I'll try my best to do these for 1026 each week, or whenever you have labs. Yeah, if you have any questions, let me know. All right, bye-bye.